but they're trivial to compute. Okay? This is the algebraic description of a dot product. If I just up and defined this to be the dot product, it's like, okay, but why aren't I just multiplying the components, like I suggested at the beginning? But the why is right here. Because as easy as this is to compute, this is the geometry of what's going on. And this is what's going to tell you about the behavior of these vectors. So you've got an algebraic representation that's very easy to compute. You've got a geometric representation, which I don't even know most of the time what the angle theta was. And yet I can start giving you all kinds of information based on this. Okay? So ease of computation, but you look at this side, interpretation, understanding what's going on. And that's going to frequently be the case when you study things. You'll have different ways of looking at stuff, and you get different pieces of information out. So, for instance, I immediately know, although it's just by chance, that the angle between V and W is 90 degrees. I immediately know that because I know their dot product is 0. Why does that follow? Well, magnitude of V, that's positive, right? Same as magnitude of W. The only way the right-hand side can be 0 is if cosine of theta is 0. One thing I forgot to mention, I forgot to put this word in. This is important. It's the smallest angle. So if I draw two vectors like this, I also have this vector possible. I want the smaller of the two. So in other words, theta is going to be between 0 degrees and 180 degrees, or 0 radians and pi. So could you just I can't even get an adequate drawing of a vector in 3 dimensions. Can I randomly look at these and see that the angle between them is 90 degrees? No. But look, that's trivial to compute. Very easy. And that's where you get a lot of power. That's why people like dot products. Furthermore, if I said A was equal to 3,7 and B was equal to negative 1, 2, A dotted with B would be negative 3 plus 14, so that's 11. The angle between A and B, when I put them tail to tail, is between 0 degrees and 90 degrees. It's acute. But if I gave you A equaling 3, 7, and B, or not B, because I have B above, so say C is equal to -1, -6, A dotted with C is -3 minus 42, that's minus 45. And I would say that this angle between these two vectors is obtuse. So between 90 degrees and 180, not including endpoints here.
I'm sorry, now how do you know that? Just by looking
But that was going to be my question.
Okay.
So how do I know? Again, look at,
Is it just the sign?
it's purely the sign, because what I know is, in general, V dot W is magnitude of V, magnitude of W, times cosine of the angle between them. Okay? Magnitudes are positive. They're square roots. So the only way the sign of the dot product is completely controlled by the SIGN sign of the cosine. And I know that cosine of theta is positive for theta in 0 degrees up to 90 degrees, that's open. I know that cosine of theta is 0 when theta is exactly 90 degrees. And I know that cosine of theta is negative when theta's in open 90 degrees up to 180 degrees. Now, I haven't drawn a thing, but I know that. We will use this when we'll use this well before this time, but at the right time, this is going to be real important to be able to understand when we start doing computations with vector fields and seeing whether or not energy is released or not as you move along a curve in a vector field. You'll be able to see with the pictures and the dot products that are used whether or not you get positives or negatives out. Okay? I can specifically tell you what the angle is. That angle is the cosine inverse of A dot C divided by magnitude of A, magnitude of C. So cosine inverse of, so A dot C we said was -45. Magnitude of A is 3 squared plus 7 squared. Take the square root. So that's what, 9 plus 49, so square root of 58 or something. Magnitude of C is 1 plus 37. Please, if asked this question on an exam, it's fine if you punch it into a calculator. But if you compute a magnitude wrong because of the arithmetic, or you punch it wrong into your calculator, and all I have is a number, and that number's wrong, you're screwed. Show your work. this is the first place I'm gonna look if your numbers are off. And if I'm seeing this and the wrong answer, I'm not gonna take off. I mean, this is not like on a job where theoretically at least you would have the time to check everything. Don't just give me numbers, because if you give me numbers, I can't give partial credit. If the number's wrong and I'm seeing here that you fouled up just a computation, maybe you lose 1 point, maybe you lose nothing. I mean, you know, where I'm going to start taking off points is if it looks like you have no clue how to compute a magnitude, that type of deal. Okay? So it's perfectly fine as far as I'm concerned to leave things like this. It's what I used to do back in the day before calculators. You know, I mean, all of this could be computed out, but this is the correct answer. So I don't really care what the angle is, what I'm driving home here. Okay? So that's your picture of dot product. Okay, now let me talk a little bit about, let's see, I can give you projections here. Yeah. Okay. Projecting a vector onto another vector. Okay. Here's a vector, I can call it F. Here's another vector. These may be in 3 dimensions. I don't care. I'll call this vector G. How much of G is in the direction of F?
Object just at 1 point.
Well, can you guys think, do you guys do that in your, you have to have done stuff like this in your engineering classes. Have you broken, okay, so let me show you the way in which you might have seen this. You have a force vector. So say that force vector looks like this. Okay? And then you break it up into this plus this. You can write I to be the vector 1, 0, and J is the vector 0, 1 if you wish. In 3 dimensions, K is 0, 0, 1. You could also write this vector as 4I plus 5J. This is what? It's the component of the force in the x direction. If I draw the picture, here is my vector F. This guy down here, this is 4, 0. That's the component of F in the x direction. And this guy up here is 0, 5. That's the component of F in the y direction. Sometimes these get denoted F sub x and F sub y. You guys seen this? Okay? So, let me jump ahead a little bit and show you where we're going. And we'll be doing this in the next chapter. So I want to talk for a moment about motion along a curve. So suppose we're moving along the curve like this, tooling around, and I pick a spot. What's going to control whether or not, as I go through that curve, do I tip over?
Momentum.
Which is what? Mass times velocity? Okay. I don't know if that's formally. I don't think so.
Because you can be static and still.
Acceleration is, I think, the guy that, is it not? Intuitively, if you're driving, if you go too fast, or if the curve is very curvy, those are the two things that come into play. And those are two components that are described by acceleration.
Are you talking about centripetal acceleration? Like around, so you're talking...
I get these things, okay.
Oh yeah, if your centripetal acceleration becomes the frictional force going around the curve, then you skid out.
Okay, so yeah. All right, so let me try and redo this discussion. Physics is not my strong point at all, so I welcome. So, centripetal force points in what direction?
Outward.
Towards the center of the circle.
Towards the center?
There's no circle.
Perpendicular to your
Perpendicular to the
motion.
Yeah.
Tangent, yeah, so if I have a tangent line to this curve, the centripetal force is going to go this way. The frictional force?
Yeah, so your frictional force is, oh gosh, it's been a while since I did this. But
frictional force is causing that.
Yeah. Yes.
Causing
yes.
this?
Well, I think.
Okay, there's also a force that's going to either pull you this way or this way, depending on if you're speeding up or not. Does that make sense? Here's the interesting thing. If you put a ball on the end of a string and you start doing this, so it's going around in a circle, I forget what percentage of people, if the string breaks at any point, where does the ball go?
It goes straight.
It goes straight. It's tangential. I think something like, I don't know, I've heard large numbers of people think it will keep going around. You know,
Curve the bullet.
there is acceleration in this direction as well, tangential. Okay? So you have acceleration acting this direction and potentially in this direction, although it may be backing up. Yeah, or it could be zero. Acceleration, when I write acceleration as a vector, these are the components in the x and the y directions. Or if it's in 3 dimensions, x, y, and z directions. That is totally irrelevant to what's going on here. Because what's important here is how much of this acceleration is in this direction and how much is in this direction. It's not helpful to look at acceleration in terms of x, y, and z directions. Not only is it not helpful, but if I move to another place, these are the directions that are important. You guys see what I'm driving?
Excuse me.
And so my question is going to be, if I have my acceleration vector, how much of the acceleration is pulling me in this direction? How much is pulling me in this direction? Now that's jumping ahead a little bit to the next chapter, where we will talk about acceleration, velocity, but we'll also talk about those questions. What controls the acceleration in those different directions? But in essence, they are what I will call projections. The projections you've likely seen up till now would be projecting the force into the x and the y, or possibly the x, y, and z direction. And what that's basically meaning is drop a perpendicular down from your f to the x. That's going to give you this vector. That's f sub x. This is orthogonal or perpendicular to it. There's some vocabulary I gotta throw at you guys. I forgot to mention. Okay? But this is what I'm after. The problem here is my vectors are not necessarily, or one of the vectors is not, I'm not trying to project G in the x and the y direction. Instead, what I want to do is to impose, I'm lousy at the drawing, a coordinate system like this. Even if I'm in 3 dimensions. Do you see what I'm saying? Do you see? And what I would like to do is write G as a sum in this direction plus something in this direction, where that's perpendicular. Do you see what I'm saying? Yeah. So I'm not real great with the physics, so sometimes it'll take me a roundabout way.
I'll talk to my physics professor tomorrow on this about this centrifugal acceleration. I should know.
Yeah, that's stuff.
But isn't on the, I thought the acceleration vector was the normal vector with the tangential vector. I thought, oh, you have to have those two components.
Yeah, that's what I drew. That's what I was.
The acceleration vector in F equals
yeah.
ma.
So if this is my acceleration vector, I'm gonna write it as this, well, this plus this.
So does not almost like become components? Just
Yeah,
components of
but they're
vectors?
not components in the x and the y direction. They're components in normal and tangential directions.
Right.
That's all. Yeah, I'm not doing anything real fancy, but the problem is, because I'm not doing it in the x and y direction, if I'm looking at this force, hey, that's trivial to write. The component in the x direction is 4, and in the y, the component there is 5. But if I randomly write down a vector, or draw a vector like G, and another vector like F, and what I want to do is to write G as a vector that's a multiple of F plus this vector.
So to relate it to what you were just, the other page, is that G the acceleration vector then? And then F
Well,
becomes
I don't have a
the-
curve here. I can't tell you what's, this is just a line. I'm just trying to point out here that this is one way in which we will see what I'm going to show you use. That's all. It's used all over the place. How much of G is in the F direction? That's basically what we're looking at. So, not limited to the stuff with acceleration, but that'll be the immediate use. Okay? Vocabulary, because it's going to creep into my language here. If V and W have a 90-degree angle between them. In other words, if V dotted with W is 0, we call V and W orthogonal to each other. Think perpendicular. There's going to be a whole bunch of different vocabulary words for things that are, in essence, perpendicular. People usually, math people, usually will use perpendicular to indicate a 90-degree angle between two lines. When two vectors are at a 90-degree angle, they will use the word orthogonal. You'll see that used again in your linear algebra if you haven't already taken it. Okay? So, what I want to do is to take a vector G and write it as a sum of a vector which is a multiple of my vector F plus something orthogonal to F. I want this picture. Okay? Now, let me explain the following, and that is that there is a formula in the book that will generate the projection. That's all well and good. There's about a 50% chance on the first test that I will ask you to compute a projection. But there is a 100% chance that I will give you a picture and ask you to draw the projection so that I know you know what these guys are. So, let me run through the pictures here. If this is a vector A and this is a vector B, the vector projection of A onto B is, and I'll call that vector P, and what I would do, I'm projecting from A onto B. I'm going to drop a perpendicular down from the end of A, and mind you, my vectors are tail to tail. This vector here is P. When people talk about the projection of A onto B, this is the vector projection. That's what they're looking for. If I have the same type of picture, so this is A, this is B. The vector projection of B onto A. I'm doing this now in the other direction. It matters what you're projecting onto what. So what I'm going to do is kind of in a dotted line, extend A. I'm going to drop my perpendicular onto that line. This vector right here, and it's a vector, so when you draw it, you have to indicate a direction. this guy right here, I'll call it Q. Two more pictures. If this is A and this is B, so now I have these angles bigger than 90 degrees. The vector projection of A onto B is the vector, I'll call it P again. So if I'm going onto B, what I'm going to do is extend the line parallel to B, drop down my perpendicular. I'm going from A onto B, so I drop the perpendicular onto B, and this right here is my vector projection. That would be P. Notice it's in the negative direction relative to B, because that angle is bigger than 90 degrees. Same picture. So if this is B and this is A, if I want to take the vector projection of B onto A, I'm gonna pull the vector A back, drop a perpendicular starting at the head of B down to A, that's that. Okay, 100% chance I will ask you to draw a vector projection of one vector onto the other. Now, I haven't done the formula. I'll do the formula in a moment. Formulas are formulas. You know, you learn them for tests, then you stash them away. You can always look them up. I mean, 50% chance you get it. But I mean, it's no sense in my mind memorizing a formula if you don't know what it is you're memorizing. And that's all in the picture. And the picture is what we are going to need. Furthermore, in a lot of instances, it's a mess to compute given what you're working with. But people will talk about these things. One more thing. The scalar projection is the magnitude of these vector projections. So the scalar projection is the magnitude or length of the vector projection. Okay. There were a few exercises in those first couple sections that asked you to do the following. So if I gave you a vector, find a vector in the same direction as V of length, let's say I want the length to be 5. Remember this exercise? This is a dopey, dinky little exercise, and we will just use it over and over, all over the place. So let me remind you. The magnitude of V here would be square root of 9 plus 1 is 10 plus 4, so square root of 14. If I take V and I divide it by the magnitude of 14, back to the magnitude of 14. If I take V and divide it by square root of 14, that gives me a unit vector, a vector of length 1. To get it to be of length 5, multiply this by 5. It's in the same direction as V because it's a multiple. Okay? So you have to make sure you divide by the multiple. Just multiplying by 5 isn't going to do it. Okay, so here's V. And say, here's my W. And I want the vector projection of V onto W. That vector, I drop a perpendicular starting at V, ending at W. Gives me a perpendicular. That vector projection is right here. My two vectors are tail to tail. There is an angle between these vectors. If I happen to know this angle, the formula we're going to work out is basically irrelevant. But if I don't know the angle, I've got troubles. So to begin with, you've got to write triangle. This vector V, you know its length, its magnitude of V. You know, or we have a symbol for this angle. This length, using just basic trig, is magnitude of V multiplying adjacent to theta, so cosine of theta. Okay? This means that my vector projection, this means I want the vector in the same direction as W, although sometimes it'll be backwards. And I want it to have this length. So what I'm going to do is I'm going to take W, I'm going to divide it by magnitude of W, and that gives me a unit vector. divide a vector by its magnitude. And then what I'm going to do is I'm going to multiply this by magnitude of v cosine of theta. Now, if my picture's like this, cosine of theta is going to be negative. So let me just write this a little bit nicer. So I would have this, and if I knew what theta was, this works just fine. I wouldn't need anything else. But if I don't know what theta is, I've got troubles. So I look for a dot product. I don't see a dot product, but I'm going to make one. I multiplied top and bottom by magnitude of W. You know, this is an old trick. Didn't change anything. And lo and behold, what I get up top is W dotted with V divided by the square of the magnitude of W. That's a number. It's multiplying the vector W. And that's the formula that will give you this vector. Okay? 50% chance, I'll ask you to compute one. The worst part of that problem is memorizing the formula. I don't memorize it. Even when I was a student, I can't memorize worth a damn. I make sure I know how to derive it. And sometimes you have to memorize. I can get around it, I do it. Some of you are going to be much better memorizers. It's the formula, but it's just that. 50% chance. I mean, you may not have me ever ask you to compute one, but I guarantee you, you will have to draw one. Okay? Notice that if the picture looks like this, W dot V is negative. And what's going to happen is this sitting in front is negative. It's going to pull you back in the other direction. Okay? The length of this vector, which is the absolute value of this, that's a scalar projection. It's either that or maybe the scalar projection keeps the sign. I can't remember. I have to look. Okay? If you took this vector, which is right here, and you subtracted it from V, what you would get would be this vector, which is the other